Have you ever wondered what happens when a star dies? Some collapse into dense neutron stars, others explode as supernovas, but the most massive among them transform into black holes. Let's delve into the birth of these celestial monstrosities. Picture a star far larger than our sun nearing the end of its life. It burns through its nuclear fuel, and the balance between gravity pulling in and energy pushing out tips. The star can't hold itself up anymore and implodes in a cataclysmic explosion known as a supernova. What remains is a dense core. If this core is weighty enough, exceeding what astronomers call the Chandrasekhar limit, an irresistible gravitational collapse occurs. The result, a black hole is born. Now imagine crossing the boundary of a black hole, the event horizon. It's a point of no return. Nothing, not even light, can escape the immense gravitational pull beyond this boundary. Venture deeper and you'll reach the heart of the black hole, the singularity. Here density reaches infinity and the laws of physics as we know them break down. This is the realm of the unknown, a place where time and space intertwine in ways we barely understand. Black holes come in various sizes, each with distinct characteristics. Stellar mass black holes, the most common type, are up to 20 times as massive as our sun. Then there are the supermassive black holes lurking at the centers of galaxies, millions to billions of times the mass of our sun. And let's not forget the elusive intermediate mass black holes, neither stellar nor supermassive, but somewhere in between. Though terrifying in their intensity, black holes are a natural outcome of the life cycle of massive stars. This is where our understanding of the universe is constantly challenged, where we stand on the brink of the unknown, pushing the boundaries of our knowledge. Isn't that a fascinating thought? Black holes are not just cosmic vacuum cleaners. They warp the very fabric of space-time, bend light, and even slow down time. The gravitational pull of a black hole is so strong that it distorts the space-time around it, like a bowling ball sitting on a stretched-out sheet. This curvature of space-time causes the path of light to bend as it passes near a black hole. This is why we can observe a phenomenon called gravitational lensing, where the light from a distant star is bent around a massive object, such as a black hole, making it look as if the star is in a different position than it actually is. But the effects of a black hole aren't limited to bending light. They also affect time itself. This is known as time dilation. The closer you get to a black hole, the slower time moves relative to someone far away. If you were to watch a clock fall into a black hole as it approaches the event horizon, it would appear to tick slower and slower until it seems to stop completely. This mind-boggling effect is a direct consequence of Einstein's theory of relativity. And then there's Hawking radiation, a concept proposed by the legendary physicist Stephen Hawking. According to quantum mechanics, pairs of particles and antiparticles constantly pop in and out of existence near the event horizon of a black hole. Occasionally, one of these particles falls into the black hole while the other escapes. This escaping particle is known as Hawking radiation. Over time, as the black hole loses energy through this process, it can gradually shrink and even evaporate completely. These properties of black holes, from space-time curvature and time dilation to Hawking radiation, reveal the extreme nature of these cosmic entities. They challenge and often defy our understanding of the universe, pushing the boundaries of our knowledge. Black holes, with their mind-bending properties, challenge our understanding of the universe. Stephen Hawking's groundbreaking work on black holes revealed a puzzling paradox that continues to baffle scientists. This paradox, known as the information paradox, arises from the intersection of quantum mechanics and general relativity. To comprehend this paradox, let's consider what happens when an object falls into a black hole. According to classical general relativity, once an object crosses the event horizon, it's destined to meet its end in the singularity, with no trace of it left behind. However, in the late 20th century, Hawking proposed that black holes can slowly evaporate over time, emitting what we now call Hawking radiation. This suggests that a black hole could eventually disappear, taking with it all the information about the objects it has swallowed. This apparent destruction of information contradicts the principles of quantum mechanics, which posits that information in a system is always preserved. This collision of principles led to the birth of the information paradox. If black holes can both destroy and preserve information, then how does the universe decide which rule to follow? This question has led to a flurry of theoretical proposals in an attempt to reconcile this paradox. One such proposal is the holographic principle, which suggests that all the information swallowed by a black hole is actually encoded in a two-dimensional surface surrounding it, similar to a hologram. This principle implies that as a black hole evaporates, this information is gradually released back into the universe. Another proposition is the firewall hypothesis. It suggests that a blazing wall of energy called a firewall exists just inside the event horizon, incinerating anything that falls in. This would imply that information is destroyed before it ever reaches the singularity, resolving the paradox but challenging our understanding of event horizons. Despite these intriguing proposals, no consensus has been reached. The information paradox remains one of the greatest unsolved mysteries in theoretical physics. This conundrum continues to push the boundaries of our understanding, reminding us of the enigmatic nature of black holes and the universe itself. If black holes are cosmic traps, their mirror images, white holes, are cosmic fountains spewing out matter and light. This statement brings us to the intriguing realm of white holes, the hypothetical time-reversed counterparts of black holes. Just as black holes devour everything within their reach, white holes are postulated to be the exact opposite. They are the ultimate no-entry zones in the cosmos, ejecting matter and energy instead of swallowing them. The strange thing about these cosmic oddities, nothing can enter a white hole from the outside, just as nothing can escape a black hole once it crosses the event horizon. White holes are rooted in the mathematics of general relativity, Einstein's theory that describes gravity. The equations allow for these peculiar entities, however, they remain firmly in the realm of the theoretical for now. Despite our best efforts, we haven't observed a white hole directly, nor have we found any substantial indirect evidence of their existence. Yet the absence of evidence is not necessarily evidence of absence. The concept of white holes remains a tantalizing possibility, one that could offer profound insights into the nature of time and the universe. If white holes do exist, they could potentially explain some of the universe's most enigmatic phenomena, such as the Big Bang. Could the birth of our universe have been a white hole, ejecting matter and energy to create the cosmos we inhabit? Moreover, if both black holes and white holes exist, could they be linked? Some theories suggest a black hole could potentially be a gateway to a white hole, creating a cosmic tunnel known as a wormhole. This is, of course, purely speculative, but it's a fascinating idea that continues to inspire scientific and philosophical debates. White holes, though hypothetical, promise to shed new light on the nature of time and the universe. They challenge our understanding, push the boundaries of our imagination, and remind us that the cosmos is far more mysterious and complex than we can ever comprehend. Could black holes and white holes be connected? Could they serve as gateways to other universes? Theoretical physics offers some tantalizing possibilities. Let's consider wormholes, for instance. These are theoretical passages in space-time that might connect distant regions or even different universes. Imagine being able to leap across cosmic distances in the blink of an eye, like jumping through a shortcut in the fabric of reality itself. But before we get too excited, we should note that the existence of wormholes remains purely speculative. While they are fascinating constructs, their stability and viability as cosmic shortcuts are yet to be determined. But the quest doesn't stop with wormholes. Scientists are also striving to bridge the seemingly insurmountable gap between general relativity and quantum mechanics, the two pillars of modern physics. General relativity beautifully describes the large-scale structure of the universe, while quantum mechanics provides a framework for understanding the behavior of particles at the smallest scales. Unfortunately, these two theories don't play well together, especially when it comes to extreme conditions like the ones inside black holes. That's where unified theories come into the picture. Consider string theory, for example. It proposes that the fundamental constituents of reality are not particles, but tiny, vibrating strings of energy. In this framework, black holes, white holes, and even wormholes could be understood as different vibrational patterns of these strings. Then there's loop quantum gravity, another promising contender. This theory suggests that space-time itself is quantized, composed of tiny, discrete loops. This could potentially resolve the singularity issue at the heart of black holes, replacing it with a transition point to another region of space-time, perhaps a white hole. Whether or not we ever find a unifying theory, black holes and white holes will continue to inspire and challenge us as we strive to understand our universe.